Hello, I'm Philip Stoten. I'm here at Productronica 2013 in Munich, and I'm joined by Mike Konrad from Aqueous. Mike, good to see you again. Thanks for stopping by.
Thanks for having me.
Just a short time since we were last together in SMTAI in Texas. One of the things I've noticed as we travel around the world is there seems to be a challenge to bring everybody together under one common standard. Is that something that's an issue in the cleaning market?
Yeah, it's a big issue in the cleaning market. We all are under one common standard. Those
right.
who utilize those standards share the standard. The challenge in our business is that standard was written in the 1970s.
Okay.
And the standard is a cleanliness standard.
Right.
It was adopted as part of the old weapon spec 6536 that was crafted out in the California desert in the 70s. It then morphed into MIL standard 2000A, and then IPC picked up the standard as one of the standards under J standard 001 and test method 650, and it hasn't changed.
Right.
And that standard was written before the word SMT or the letters SMT meant surface mount technology. There was no surface mount when that standard was written. So unfortunately, that's the standard we have.
And does that standard identify particulate size, or how does it work, and how would it apply to modern manufacturing?
The standard is based on the allowable amount of contamination that can be present on a board. And that standard utilizes a particular technology called the ROSE tester, or resistivity of solvent extract tester. Basically, it's a bulk extraction tester. We put a board into a machine, extract all the contamination, measure how much contamination there is, by electrical resistance. And then, to make matters more confusing, translate that number into micrograms of sodium equivalent per area of board unit, of board size. So it basically means how much salt would we have to add to the test solution to make the electrical conductivity change as much as it changed with the contamination. So sodium is an equivalency, it's not a literal term. The problem is the IPC standard allows 10 micrograms of sodium equivalent per square inch of board surface, or 1.56 micrograms per centimeter square. And nowhere in the standard, because this wasn't relevant in the 70s, does it state it depends on where the board is going to go, it depends on the operational environment of the board, it depends on the density or the spacing between components. It's just 10 micrograms of sodium per square inch. And what we find today is the amount of there's always contamination on a board. Unless the board is cleaned, there's always some degree of contamination, either from a combination of board fabrication residues, component fabrication residues, transfer contaminants, assembly residues, fingerprints, and then flux, maybe no clean flux. There's always some degree of contamination on a board. And the amount of tolerable contamination varies depending upon
application,
density of the board and spacing. A certain amount of contamination between a small gap is worse than the same amount of contamination between a large gap. So, and some contamination, most of the contamination causes other reactions to take place under certain other environments, such as humidity, higher voltages, etc.
All stuff that wasn't relevant in the 70s.
All stuff that was more consistent in the 70s, right? Back in the 70s, we could drive Mack trucks underneath the component, and you could see light coming out the other side. Now, QFNs and all these different components that are extremely dense, miniaturization, lead-free changed everything with soldering reflow temperatures going higher, burning more contaminants onto the board, making it more difficult to clean. So now the amount of tolerable contamination varies. So one can say 10 is a good number on this style board with this density in this operational environment, and that same number on a more densely populated board installed into a more harsh environment could kill it. But 10 is a number everyone uses.
Yes, because that's the number from the IPC standard. So we hear this question, how clean is clean? But my question would be, is clean enough?
I think
because we're defining clean by that IPC standard.
I think the properly phrased question is exactly what you said. Is how clean is clean enough? How clean do I have to be? And the answer to that question
is not
brings
one
on
number,
more questions. It's never one number. Well, if it can be. If someone were to put me in a corner and say, what's the number for everybody, and I don't know the application, I've never seen the board.
You've got to go.
Then how clean is clean? 0.0. 0.0 is clean. You can't argue that.
Okay.
But
then they asked to order a machine that does 0.0 and you can't supply one.
Well, no, 0.0 is perfectly obtainable.
Okay.
In a well-controlled process, 0.0 is reasonable.
Okay.
But arguably, one doesn't need 0.0. One can live with 0.1 or 0.2, and maybe even 10, maybe even 100. It just depends on a number of factors. So when we say how clean is clean, and then people reject 0.0 because that's just a flippant answer, right? It's true, but it's flippant. Then we say, okay, you got to factor in several things. How clean is clean enough brings in a few more questions. One is, what's the cost of failure? Is the cost of failure you get more business? Planned obsolescence? Is the cost of failure death and destruction? Loss of reputation?
Mission critical.
Litigation? Right. The other is, the way the ROSE testers work is they just take all the contamination and divide it evenly across the board.
Right.
Well, we all know common sense would say the contamination probably wasn't evenly spread. It was probably higher here, lower here, and it averaged out. So one has to look at the geographic density of the board and how consistent it was.
So a big clean space over here doesn't make this bit clean, does it?
Right. If you have a big empty area here and a dense area here, then the number is probably twice as much as it's showing because it averaged out. So you look at the density consistency, and then you look at the environment that the board's going to go in. If it's going to be buried in the ground, is it going to go up into space? Is it going to go on a space mission where it's impossible to repair? Is it going into a human? Is it going into a Game Boy? All these things. And then the environment that the boards are going to be put in. How easy is it to repair? What kind of environment? Something going in a router on a server farm is always going to see plus or minus 1 degree and a relative humidity that's pretty low. Something going downhole in Houston into an oil well is going to see much harsher conditions. Something in an unpressurized part of an aircraft is going to see major thermal excursions. And that all varies. That all changes how acceptable residue is.
So we're not happy with what we got.
Right.
What are we going to do about it, Mike?
Well, we can wait for IPC to
We've been waiting since 1970
We've been waiting
something?
for a long time. And I don't know if it's reasonable to expect a number. I don't know. Because are we going to tell Nintendo that their number is the same as Medtronic? Right? So I think that we need to, first of all, it's important to know what the number is. Boards need to be tested. We need to know what the number is and figure out if there's a way to make it lower. And then figure out if that number is satisfactory to that board. And one of the ways to do that is to do some accelerated age testing, steam testing, put it in a climate chamber, accelerate the age several hundred hours in a high humidity, 85, 90 relative humidity, and undercurrent, and see if bad things happen. If bad things happen, or we're progressing toward bad things happening, then we have to drive down the cleanliness number. So many people will reject the idea of performing cleanliness tests because the number is irrelevant. The number's relevant. It's the prediction of what number is safe, which is not always relevant. Test, see the number, figure out if your boards react well under that number, under the conditions they're designed to be placed under, and then keep testing to make sure that number doesn't change. That's how to do it.
So we get that number right, or we get a formula right, or we have a group of numbers for a different application. What does that mean to a capital equipment supplier like Aqueous?
It means we sell testers. It means we
sell
sell cleaners
instead of cleaners, or
we sell both. Our cleaners test as well. The idea of a tester.
Can you just dial in?
Yeah, you can dial in how clean you want, and the machines will clean until the boards are clean. The idea of a tester is to validate the process. If there's no problems with the boards from a reliability standpoint, and you always get a number, say the number is just for the sake of discussion, 7. You always get a 7, there's never any problems. Then keep testing. If you get a 12 one day, stop the presses, figure out what's causing that 12, because you don't, now you're in foreign territory, you don't know if 12 is going to cause a problem. And then figure out how to mitigate, fix the issue, and get back to 7. If you're getting if you always get 0.1s and you never have trouble, stick with 0.1s. But it starts with knowing what the number is. And there's a lot of testers. There's several brands of testers. They're not expensive, and they produce nearly instant results. And it all starts with knowing the number. And then backing into figuring out if that number produces reliable boards, and then constantly monitoring that number. Okay. Most people don't clean incoming boards, and most people would be surprised to see how dirty bare boards can be. Some people wouldn't want to eat off them, much less build assemblies on them. So because boards are coming in an unknown level of cleanliness, and then assemblers are piling on residues beyond that, it's very important to know what that number is and whether it has changed. And one of the other things to remember is no clean flux. We're proponents of no clean flux. More than 80% of our customers are cleaning no clean flux. So we have no argument with the concept of no clean. More than 53% of all users of no clean flux are reported to be cleaning the flux. So it's the number one cleanable flux, or clean flux. One of the problems is the name of no clean flux. People see the word no clean and they think it's an instruction. It really should be entitled low residue flux. Because it does leave a residue, and in many cases it's benign. In some cases it's not benign. In some cases it's adding in a cumulative fashion to the total contaminant count on the board. Because when you don't clean flux, you don't clean anything. So if people think of no clean as low residue, they know there is residue on the board, then
they know what the cleaning challenge is.
Then they know if that residue is appropriate for the board or inappropriate.
And they know what the number is. Just coming back to the number for a final time, without talking about what the number actually is it then down to you to work with your competitors to formulate that number? And are you all singing from the same song sheet? Does everybody have this view about having a number that isn't that IPC 1970s number?
I don't know. We certainly have been beating that drum for a long time. And we educate our customers. We teach it in our workshops. It's a big part of our workshop. I taught it yesterday here at the show floor. I would think that other manufacturers of similar type of equipment certainly know that. But because we're the only company that manufactures testers and cleaners, we have a different perspective because we have the ability to share the bad news with the customer that the boards are too dirty and point them to a solution for it, whether it's ours or someone else's. We have the knowledge of cleaning and the knowledge of testing. Usually those are separate companies and they don't usually
mix
that well.
Okay, well, fascinating stuff, Mike. We should really push that on, and you should really be able to report to me at some point that there is some progress.
I'll let you know the standard. You'll be the first to know when the standard changes.
Thank you. Thanks for your time.
My pleasure. Thanks, Phil.
Thanks a lot.